2022, 3 physicists stood in Stockholm and collected a Nobel Prize for proving that the universe is not locally real. The experiments were definitive. The loopholes were closed. The mathematics was airtight. Bell's inequality, the single most consequential line in all of physics, had been tested, confirmed, and filed away as settled science. That was the end of the story. Except it was not, because in August of 2025, one of those 3 Nobel laureates put his name on a paper that should not exist. A paper published in Science Advances reporting that Bell's inequality had been violated at greater than 4 standard deviations above the classical bound, and the photons that violated it were not entangled. Before we dive in, if you want to support the channel and get exclusive content on all things space and physics, check out our Patreon. Link is in the description. I need you to understand what that sentence means because it sounds technical and dry, but it is neither. For 60 years, every physicist on Earth agreed on at least one thing about Bell's inequality. You cannot violate it without entanglement. That was not a guess. That was not a conjecture. That was a proven mathematical theorem, published in 1989 by Reinhard Werner, accepted by the entire community, reproduced in every graduate textbook in quantum information theory. It is as close to a mathematical certainty as physics gets. Separable states, states without entanglement, cannot produce correlations strong enough to break the Bell bound. Period. And then Kai Wang, Zhao Huaho, Kai-Yi Qian, Mario Kren, Marcus Aspelmeyer, Anton Zeilinger, and colleagues at Nanjing University, the Max Planck Institute for the Science of Light, and the University of Vienna published a peer-reviewed paper saying it happened anyway. The CHSH parameter they measured was S equals 2.342, plus or minus 0.051. The classical bound is 2. They exceeded it by more than 4 sigma, and the co-author list includes Anton Zeilinger, the same Anton Zeilinger who won the 2022 Nobel Prize in Physics, the same Zeilinger whose group in Vienna produced one of the 3 definitive loophole-free Bell tests in 2015, the same man who stood in Stockholm in a white tie and accepted a medal for proving that Bell's inequality is violated by entangled particles. His name is now on a paper that says entanglement might not be required. And if that number holds, if it survives the scrutiny that has already begun, then non-locality is not a trick that entangled particles perform. It is something the universe does to everything, everywhere, whether you prepare for it or not. That sentence is going to take on a weight you do not expect by the end of this, and I want you to remember it. Within 6 weeks of that paper appearing, 3 independent groups of theorists published rebuttals. 3 separate teams at 3 separate institutions, each arguing from different angles that the Wang result is an artifact. Not a breakthrough, not a revolution. An artifact of post-selection, non-standard normalization, and a subtle confusion between 2 different kinds of entanglement. One of those rebuttals came from Marek Zukowski, a physicist at the University of Gdansk who co-authored Zeilinger's own 1993 entanglement swapping proposal. A man who helped build the intellectual foundation that Zeilinger's career stands on, just published a paper saying Zeilinger's latest result does not mean what it claims to mean. And as of right now, April 2026, no response from the Wang group has appeared. No defense has been published. No rebuttal to the rebuttals. The paper sits in Science Advances, peer-reviewed and published, while 3 separate critiques sit on arXiv, saying it is wrong. The most important active dispute in quantum foundations is playing out in preprints that almost nobody outside the field has read, and nobody is talking about it. That is the situation. A rule that was never supposed to break appears to have broken, or appears to have appeared to have broken, and the physics community cannot agree on which one it is. The boundary between a locally real universe and a non-local one, the single most consequential line in all of physics, is being re-examined right now by the very people who drew it. And the public version of the story, the one where Bell's theorem was settled and filed away, is already out of date. But to understand why any of this matters, why a number slightly above 2 should keep you up at night, you need to understand what Bell's inequality actually says. And it does not say what you think it says. The story starts in Belfast, 1928, with a boy whose family could not afford to send him to grammar school. John Stuart Bell was born on the 28th of July, 1928, the second of 4 children in a working-class family in Belfast, Northern Ireland. His father, also named John, worked manual trades. His mother, Annie, had not finished high school. Neither had his sister Ruby, nor his brothers David and Robert. They called him Stuart at home to distinguish him from his father, and when he was 11 years old, he told his family he was going to be a scientist. The prestigious grammar schools were financially out of reach, so he attended Belfast Technical High School and he graduated at 16, which was almost unheard of for someone from his background. He earned 2 bachelor's degrees from Queen's University Belfast, one in experimental physics in 1948 and a second in mathematical physics in 1949, both with first-class honours. He completed a PhD in nuclear physics and quantum field theory at the University of Birmingham under Rudolf Peierls in 1956. His thesis included an independent proof of the CPT theorem, but Gerhard Luders and Wolfgang Pauli published their version first by a matter of months, and they received the credit. That pattern, Bell arriving at the right answer and someone else getting the recognition, would define his entire life. He married physicist Mary Ross in 1954. They had met doing accelerator work at Malvern. In November 1960, both Bells moved to CERN in Geneva, where John's official job was particle physics and accelerator design. His most celebrated day job contribution is the Adler-Bell-Jacquiot anomaly of 1969, co-discovered with Roman Jacquiot, which explained why the neutral pion decays into 2 photons despite a symmetry that should forbid it. ABJ anomalies now pervade modern quantum field theory. That alone would have been a distinguished career. But the work that changed physics, the work that is right now at the center of the 2025 controversy, was not his job. It was his hobby. He did it on evenings and holidays during a 1963-64 sabbatical at Stanford, the University of Wisconsin-Madison, and Brandeis. His colleagues at CERN, the people who saw him every day, did not know what he was working on at night. I am telling you this not because it is interesting background, but because it connects directly to the rule that may or may not have broken in Nanjing in 2025. Bell's inequality did not emerge from the mainstream of physics. It emerged from the margins, from a man working in secret on a question his profession considered disreputable. And the fact that it is now the most tested, most confirmed, most consequential inequality in all of physics is one of the great ironies of 20th century science. The question Bell was asking was not new. Einstein had asked it in 1935 in the famous EPR paper co-authored with Boris Podolsky and Nathan Rosen. Einstein's argument was straightforward. Quantum mechanics says that two particles can be entangled in such a way that measuring one instantly determines the state of the other, regardless of distance. Einstein found this absurd. He called it spooky action of a distance, and he was convinced it meant quantum mechanics was incomplete. There must be hidden variables, pre-existing properties that the particles carry with them that determine the outcomes in advance. The correlations are not spooky. They are just correlations. Like reaching into a box of gloves, pulling out a left glove, and immediately knowing the other one is right. No action at a distance required. Just pre-existing information. And Einstein's argument was reasonable. It was not the argument of a crank. It was the argument of the most celebrated physicist of the 20th century, grounded in the same intuitions about locality and causation that every engineer, every pilot, every builder relies on every day. If Einstein was right, quantum mechanics was a perfectly good statistical tool like thermodynamics, but it was not the final story. Underneath the probabilities, there was a clockwork, hidden gears, a deeper reality that quantum mechanics was too coarse-grained to see. For nearly 30 years, Einstein's argument stood as a philosophical position. Nobody could prove or disprove it. The prevailing attitude was Bohr's response to EPR, which most physicists accepted without examining too carefully. Bohr's reply was notoriously obscure, written in a style that even sympathetic readers found impenetrable, and the profession largely moved on by adopting the unspoken consensus that the foundations were someone else's problem. The broader culture was what would later be called "shut up and calculate," a phrase coined not by Feynman, as is commonly attributed, but by David Mermin in a 1989 Physics Today column, mocking the very culture that had made Bell's work invisible. And here is something that rarely gets said in popular accounts. The reason nobody could resolve Einstein's argument for 30 years was not that the argument was too subtle. It was that nobody tried. The physics community, flushed with the successes of quantum electrodynamics, transistors, nuclear energy, and the emerging Standard Model, had decided that foundational questions were beneath them. Asking whether quantum mechanics was complete was considered, in the professional culture of mid-century physics, roughly equivalent to asking whether gravity was real. It was not just a waste of time. It was an indicator of confused thinking. And this professional stigma was enforced not by formal decree, but by the slow, quiet mechanisms that every academic knows: the withheld invitations, the skeptical tenure letters, the papers that reviewers returned with the comment that the physics community has moved past these questions. Bell walked into that culture with a question that the culture had decided was illegitimate, and he answered it. And here is the misconception I need to correct before we go further, because it matters for everything that follows. Bell's theorem does not say the universe is weird. It does not say quantum mechanics is spooky. It does not say particles behave strangely. Those are pop science translations that strip out the one thing that actually matters. What Bell's theorem says is this: the universe is not locally real. Those three words have a precise mathematical meaning, and the difference between the universe is weird and the universe is not locally real is the difference between a curiosity and an earthquake. Local realism is the conjunction of two assumptions. Locality means that what happens here cannot instantaneously affect what happens there. If I flip a switch in this room, It cannot change the reading on a detector in another galaxy right now. Influence propagates at the speed of light, or slower. Realism means that physical properties exist whether or not you measure them. The electron has a spin before you check it. The photon has a polarization before it hits the detector. The moon is there when nobody is looking at it. These two assumptions are so natural, so deeply woven into every intuition you have ever had about the physical world, that rejecting either one of them feels like rejecting sanity. And Bell proved, mathematically, that you have to reject at least one of them. His proof is breathtakingly short. The original paper on the Einstein-Podolsky-Rosen paradox, published in the journal Physics Physique Physica, Volume 1, Number 3, pages 195 through 200, in 1964, is 6 pages long. Bell started from Bohm's 1952 reformulation of the EPR argument, assumed locality, assumed that hidden variables determine the outcomes in advance, and derived an inequality, a mathematical ceiling on how strongly correlated two measurements can be if local realism is true. And then he showed that quantum mechanics predicts correlations above that ceiling. The implication is absolute. If you accept locality and realism, you get the inequality. If you do the experiment, you violate the inequality. Therefore, locality and realism cannot both be true. At least one of them is wrong. And there is no escape clause. There is no loophole in the math. The theorem is as airtight as any result in mathematical physics. Bell chose an obscure journal deliberately. He was aware of the taboo. John Clauser, who would later perform the first experimental test, recalled that Bell's paper was originally published in the terminal issue of an obscure journal and in an underground physics newspaper called Epistemological Letters. It was not until after the 1969 CHSH paper and the 1972 Friedman-Clauser results were published in Physical Review Letters that Bell finally openly discussed his work. He was aware of the taboo on questioning quantum mechanics foundations and had never discussed it with his CERN co-workers. Think about that for a moment. The man who proved the most important result in quantum mechanics since the Schrödinger equation did not discuss it with his colleagues because the question itself was considered unprofessional. The result sat in a dying journal, receiving 92 citations in its first 18 years, while the physics community looked the other way. But the math was the math, and eventually someone had to test it. In 1969, while still a graduate student at Columbia University, a physicist named John Clauser teamed up with Michael Horn, Abner Shimoni, and Richard Holt to turn Bell's thought experiment into something you could actually build in a lab. Their paper, published in Physical Review Letters Volume 23, page 880 in 1969, reformulated Bell's inequality into what is now called the CHSH inequality. The letters stand for their initials. And the inequality says this: define a quantity S, constructed from 4 sets of correlation measurements between 2 particles using 2 different measurement settings on each side. If local realism is true, S must be less than or equal to 2. If quantum mechanics is right, S can go as high as 2 root 2, which is approximately 2.828. That number, 2 root 2, is called the Searelson bound, and it represents the maximum quantum violation. So the test is clean. Measure S. If it is at or below 2, local realism survives. If it exceeds 2, local realism is dead. But Clauser had to actually do the experiment. And this is where the institutional story gets ugly. His faculty at Columbia told him that testing quantum physics would destroy his career. Those are not my words. Those are Clauser's words, given in interviews decades later. And it was not just Columbia. While Clauser was performing the experiment at UC Berkeley, Caltech's Richard Feynman was highly offended by his effort and told him that it was tantamount to professing a disbelief in quantum physics. Think about that. The man widely regarded as the greatest physics communicator of the 20th century told a young experimentalist that testing a mathematical theorem was an act of disbelief, not testing a speculation, not testing a fringe theory, testing a mathematical derivation that makes a precise, falsifiable prediction about measurable correlations. But Clauser did it anyway. In a basement laboratory in Burge Hall at Lawrence Berkeley National Laboratory in 1972, Clauser and graduate student Stuart Friedman excited calcium atoms with a hydrogen arc lamp to produce pairs of photons at 551.3 nanometers and 422.7 nanometers. They separated the photons by about 5 meters. They measured polarization correlations at various angles. The setup was, by modern standards, primitive. A hydrogen arc lamp is not a laser. The photon production rate was low. The detectors were slow. The experiment took months of painstaking alignment, data collection, and troubleshooting in a basement that had no air conditioning and no particular institutional support. Clauser had privately bet $2 against Yakir Aharonov's $1 that quantum mechanics would lose. He expected local realism to win. He expected Bell's inequality to hold. He genuinely believed that when the data came in, it would vindicate Einstein and expose quantum mechanics as incomplete. That is an important detail. Clauser was not a true believer testing a prediction he knew would succeed. He was a skeptic who put his money literally on the other side. And the data changed his mind. It did not hold. Friedman and Clauser, Physical Review Letters, Volume 28, page 938, published the 3rd of April, 1972, reported a violation of 6.3 standard deviations. Clauser mailed Aharonov a $2 bill along with his preprint. Years later, when asked about the result by the Associated Press after winning the Nobel Prize, Clauser said, "Why this happens, I have not the foggiest. I have no understanding of how it works, but entanglement appears to be very real." That admission, from a man who spent his career trying to disprove entanglement, is worth more than 1,000 textbook assertions. He tested it. He lost his bet. And 50 years later, standing in Stockholm, he still could not explain what was happening, only that it was happening. And here is the detail that makes the institutional story sting. Holt and Pipkin at Harvard ran a similar experiment and got the opposite result, supporting local realism. They never published it. Fry and Thompson at Texas A&M confirmed Clauser's violation in 1976. The data was clear. Local realism was wrong, but the profession barely noticed. The next person to push was Alain Aspect, born the 15th of June 1947 in Agen, France. He had just returned from 3 years teaching physics in Cameroon as an alternative to military service. He walked into Bell's office at CERN in 1975 to describe an experiment he wanted to run, one with time-varying polarizers that could address the locality loophole. The concern that the measurement settings on one side might somehow leak to the other side before the photon arrives. Bell's first question was not about the physics. His first question was, do you have a permanent position? He was warning Aspect that working on Bell tests could end a career, that the physics establishment considered this question, the most fundamental question about the nature of reality, to be professionally dangerous. Aspect did have a tenured position, and he proceeded. Over 1981 and 82, Aspect's group at the Institut d'Optique in Orsay ran 3 experiments, each more definitive than the last. The challenge Aspect set himself was specific. All previous Bell tests, including Clauser's, had used fixed polarizer settings. The settings were chosen before the experiment ran and did not change while the photons were in flight. That left open a theoretical possibility, however unlikely, that the source could somehow know the settings in advance and adjust the hidden variables accordingly. It was called the locality loophole, and it haunted every result. Aspect's solution was acousto-optical switches. These are devices that use sound waves in a crystal to redirect a light beam. By driving the crystal at roughly 50 MHz, Aspect could change the effective polarizer setting every 10 nanoseconds, which is fast enough to switch settings while the photons were in flight between the source and the detectors. The photons had a flight time of about 20 nanoseconds. The switching was faster than the flight. So even if the source had somehow read the settings at the moment of emission, those settings would change before the photons arrived at the detectors. The source would have been fooled. Building this apparatus took years. Aspect was working at a French government research laboratory, not a lavishly funded university. The equipment was built by hand. The alignment was painstaking. He later recalled that many of his colleagues thought the experiment was a waste of time, not because it would fail, but because they already knew quantum mechanics was right and saw no need to test it. The attitude was that Aspect was confirming the obvious, which is the kind of criticism that sounds reasonable until you remember that nobody had actually done the test. The third experiment, Aspect, Dalibard, and Roger, published in Physical Review Letters, Volume 49, page 1804, on the 20th of December, 1982, violated Bell's inequality by 5 standard deviations and partially closed the locality loophole. An earlier run with fixed 2-channel polarizers had exceeded the Bell bound by more than 40 sigma. 40 sigma, that is not a marginal result. That is a statement. Local realism was not just wrong, it was catastrophically wrong. The universe violates Bell's inequality with a kind of enthusiasm that is difficult to overstate. But 2 loopholes stubbornly survived for 3 more decades. The detection loophole, meaning that if your detectors are not efficient enough, you only see a biased subset of photon pairs, and a local hidden variable model could in principle exploit that bias to fake a violation. And the locality loophole, meaning that if the measurement settings are chosen before the photons are fully separated, information about the setting choice could in principle leak between the 2 sides at the speed of light. For 30 years, these loopholes gave local realism one last place to hide. Not a comfortable place, not a likely place, but a place where a sufficiently determined local realist could still point and say, you have not ruled out every possibility. And in science, especially in a field as philosophically loaded as this, every possibility matters. And then, in a single 4-month window in 2015, 3 groups closed both simultaneously. The first was Ronald Hansen's group at Quitech in Delft, Netherlands. Henson and colleagues published in Nature, volume 526, pages 682 through 686, October 2015. Their setup was extraordinary. They used 2 nitrogen vacancy centers, single atomic defects in diamond crystals, placed in separate laboratories, 1.3 kilometers apart on the Delft University campus. They could not directly entangle the diamonds because the distance was too great for a direct quantum link. Instead, they used a technique called entanglement swapping. Each diamond emits a single photon entangled with its local nitrogen vacancy center. The 2 photons are sent to a central station halfway between the labs, where a joint measurement projects the 2 distant diamonds into an entangled state. The diamonds have never interacted. The photons that mediated the entanglement have been destroyed by the measurement. And yet, the diamonds, sitting in separate buildings over a kilometer apart, are now entangled. The catch was the event rate. Entanglement swapping with nitrogen vacancy centers is astonishingly inefficient. The probability of a successful entanglement event in any given attempt was roughly 1 in a billion. Hanson's team ran the experiment for 18 days around the clock, accumulating just 245 usable events. 245 data points collected over 432 hours to answer the most fundamental question in physics. They measured S equals 2.42 plus or minus 0.20. The p-value was 0.039. Local realism was rejected. Barely, by the skin of its teeth, but rejected. The second was Zeilinger's own group in Vienna, Justina and colleagues. Physical Review Letters, Volume 115, Article 2, 50401, December 2015. This was a photonic experiment, more in the tradition of Clauser and Aspect, but with modern technology that neither of them could have dreamed of. Entangled photons with detectors 60 meters apart, placed in the sub-basement of the Hofburg Castle, the former Imperial Palace. Detection efficiency above 75%, achieved using superconducting transition edge sensors cooled to within a fraction of a degree of absolute zero. The p-value was far below 1 in a million. This was Zeilinger's experiment. Remember that name, remember that group. They will return. The third was the NIST Boulder team led by Sai-Woo Nam and Krista Shalm. Physical Review Letters, Volume 115, Article 2, 50402, also December 2015. Photons separated by 185 meters. Superconducting nanowire, single photon detectors at telecom wavelengths. They reported a probability under local realism of 3.74 times 10 to the negative 31. That is an 11.5 sigma result. For context, the discovery of the Higgs boson was declared at 5 sigma. The NIST result was more than twice as significant as the discovery of a new fundamental particle. And then, because even 3 simultaneous loophole-free tests were not enough for some, Zeilinger organized the Big Bell test in 2018, published in Nature, Volume 557, page 212. More than 100,000 human volunteers in 12 countries, connected through a website, generated random sequences by mashing buttons as fast as they could. These human-generated random sequences were used as measurement settings in 13 Bell experiments running simultaneously around the world. The idea was to close even the most exotic remaining loophole, the freedom of choice loophole, the concern that the random number generators used in previous tests might themselves be correlated with the hidden variables through some unknown physical mechanism. By using human free will as the source of randomness, Zeilinger was betting that human choices are genuinely free, or at least genuinely unpredictable. The result confirmed the violation once again. 3 experiments in 2015, a massive global collaboration in 2018. Every loophole closed simultaneously. Local realism was not just dead, it had been dead for decades. And now, even the last hiding places had been sealed. And then, because the physics community sometimes operates at a pace that would embarrass geological processes, the Nobel Prize committee took another 7 years. Thomson Reuters had flagged the trio of Aspect, Clauser, and Zeilinger as likely laureates back in 2011, 11 years before the call came. The physics community had known for decades who deserved the prize. The question was never whether the work merited recognition. The question was whether the Nobel Committee would ever get around to recognizing foundational quantum mechanics, a field it had historically treated as philosophy rather than physics. Year after year, the prize went to other discoveries: condensed matter, astrophysics, particle physics. The people who had answered the most fundamental question about the nature of reality waited while the committee honored other work. On the 4th of October 2022, the Royal Swedish Academy of Sciences announced the Nobel Prize in Physics for Alain, John Clauser, and Anton Zeilinger for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. The prize was 10 million Swedish krona, split 3 ways, 58 years after Bell's paper, 50 years after Bell's death. The Nobel Committee chair, Anders Erbach, said a new kind of quantum technology is emerging. Committee member Eva Olsen said the laureate's work had opened doors to another world and shaken the very foundations of how we interpret measurements. The presentation speech at the ceremony observed that the circle began in Austria and was closed in Austria, referring to the fact that Schrödinger, who coined the word Verschränkung, entanglement, in 1935, was Zeilinger's Austrian predecessor. Bell died on the 1st of October 1990 of a cerebral hemorrhage in Geneva. He was 62 years old. He had just returned from accepting honorary doctorates at Queen's University Belfast and Trinity College Dublin. Multiple sources, including the definitive Oxford biography by Andrew Whittaker and the MacTutor mathematical biography, report that he had been nominated for the 1990 Nobel Prize in Physics without his knowledge. Nobel rules forbid posthumous awards. The man who proved the most important theorem in quantum mechanics of the second half of the 20th century died without the prize. At the Stockholm banquet on the 10th of December 2022, Alain spoke for all 3 laureates. He opened by saying that recognition should go first to the late John Stuart Bell, without whom they would not be there. He then recalled Bell's first words to him in 1975. "Do you have a permanent position?" And the presentation speech at the ceremony noted, "Sadly, neither Bell nor Friedman is still with us today." Stuart Friedman, Clauser's graduate student who co-ran the 1972 experiment, had died in 2012. Writing in the Proceedings of the National Academy of Sciences, Gilles Brassard, the co-inventor of the BB84 quantum cryptography protocol, was blunter. He wrote that it was very clear to him that it should have been theoretician John Bell. for one half of the prize, with the two experimentalists sharing the other half. But of course, this was not possible, because the Nobel Committee waited decades too long before recognizing the importance of Bell's work, and also because of his untimely death. Bohm, exiled by McCarthyism, de Broglie silenced by the Solvay consensus, Bell working on his theorem in secret because his colleagues considered it unprofessional. Clauser told his career would be destroyed. Aspect warned to make sure he had tenure. There is a pattern here, and the pattern has nothing to do with the quality of the physics. But here is where the story refuses to stay in the past. Because the rule Bell proved, the inequality the Nobel honored, the result that 3 experiments confirmed beyond any doubt in 2015, that rule is now at the center of an active dispute. And the dispute is not coming from outsiders, from cranks, from people who do not understand the physics. It is coming from the inside, from the same institutions, the same research groups, the same intellectual lineages that built Bell testing into the precision science it is today. And there is something the loophole-free tests could not close. Not a loophole in the experiment, a loophole in the assumption that entanglement is required at all. To understand the 2025 result, you need to understand what the word entanglement actually means in the context of Bell tests, because the popular version of the word has been diluted to the point of uselessness. Entanglement, in the precise quantum mechanical sense, means that 2 or more particles are in a joint quantum state that cannot be written as a product of individual states. Mathematically, if Alice has particle A and Bob has particle B, the combined system is entangled if and only if the state of the pair cannot be expressed as state of A times state of B. If it can be factored that way, the state is called separable. And Werner's 1989 theorem, Reinhard Werner, Physical Review A, Volume 40, page 4277, proves that separable states admit a local hidden variable model and cannot violate any Bell inequality. Period. This is not a conjecture. It is a proven mathematical result. It is as solid as any theorem in linear algebra. If the photons are not entangled, they cannot violate CHSH. That is what Werner proved. That is what every graduate textbook in quantum information says. And that is what the Wang experiment appears to contradict. The experimental setup is an evolution of something called the Zhu-Wang-Mandel geometry, first demonstrated in 1991, generalized to 4 photons through a framework developed by Kren, Hochreiner, Lahiri, Erhard, and Zeilinger himself, published in Reviews of Modern Physics, Volume 94, Article 025, 007 in 2022. The framework is called path identity, and the core idea is this. You take 4 non-linear crystals. Each crystal can undergo a process called spontaneous parametric down conversion, where a single high-energy photon enters the crystal and, with very low probability, splits into 2 lower-energy photons. This is a well-understood quantum optical process. It is the standard method for producing entangled photon pairs. The key word there is can. In most setups, each crystal produces its own pair, and the pairs from different crystals are independent and unentangled. But the Wang experiment does something subtle. They overlap the optical paths of photons from different crystals. They align the geometry so that if you only look at the output photons, you cannot tell which crystal they came from. The which source information is erased by the path alignment. And when that happens, something extraordinary occurs. The probability amplitudes from the different crystals interfere, not the photons, not the particles, the amplitudes, the mathematical objects that describe the probability of different outcomes. They add and subtract in a way that depends on two phase settings, alpha and beta, which the experimenters can control. I need to pause here because the distinction between photons interfering and amplitudes interfering is one of those things that sounds pedantic, but is actually the entire point. When two water waves meet, the physical water rises and falls. The waves are real physical disturbances in a real physical medium. When two photons interfere in a standard double-slit experiment, something similar seems to happen. The detection pattern shows bright and dark bands, and for decades, people described this as photon waves interfering with each other. But in the Wang experiment, the interference is not between photons meeting each other. It is between mathematical possibilities. Crystal 1 could produce a photon pair. Crystal 2 could also produce a photon pair. If the paths are aligned so that you cannot tell which crystal fired, the quantum formalism says you must add the amplitudes for both possibilities before computing the probability. And when you do that, you get interference terms, constructive in some phase configurations, destructive in others. The interference is between things that could have happened, between alternative histories of the photon production process, and it shows up in the statistics of the detection events. This is called frustrated down conversion, and the Zeilinger group has been exploring it for years. The word frustrated refers to the fact that the down conversion process in one crystal can be suppressed, frustrated by the alignment with another crystal. A crystal that would normally produce photon pairs at a certain rate can have its output reduced to nearly zero if a second crystal is aligned so that the amplitudes cancel. The photons are not blocked by a physical barrier. They are cancelled by a mathematical interference between possibilities, between things that did not happen. The universe, in this picture, does not just respond to what happens. It responds to what could have happened. And the difference between those two ideas is the difference between a classical world and a quantum one. Wang and colleagues then construct a CHSH-like quantity from the coincidence rates measured at different phase settings. They scan alpha and beta, record 4 photon coincidence events, and compute S, and they get 2.342 plus or minus 0.051, greater than 2, greater than the classical bound, at greater than 4 sigma significance. And they claim the photons are not entangled. Now I need to address a point of confusion that has already appeared in the online coverage of this result, because getting it wrong here leads to getting everything else wrong. The phrase nonlocality without entanglement is not new. In 1999, Charles Bennett, David DiVincenzo, Christopher Fuchs, Tal Moore, Peter Shaw, John Smolin, and William Wouters published a paper in Physical Review A, volume 59, page 1070, with exactly that title. But their result was about something completely different. What Bennett and colleagues showed was that there exist sets of product states, completely unentangled states, that can be perfectly distinguished by a joint measurement, but cannot be reliably distinguished by any sequence of local operations and classical communication. So there is information in the global state that local parties cannot extract. That is a form of non-locality in the information theoretic sense, but it has nothing to do with Bell violations. Nobody's inequality is violated. Nobody's correlations exceed any bound. The Bennett result is about information access, not about measurement correlations. The Wang claim is categorically different. Wang claims a CHSH violation, a violation of Bell's inequality, the actual inequality with the actual number S exceeding 2. And Werner's 1989 theorem says that is impossible for unentangled states. So when you hear non-locality without entanglement and think the idea has been around since 1999, you are comparing two fundamentally different claims. One is about information, the other is about correlations. One is consistent with Werner's theorem. The other, if correct, would challenge it. Their argument is specific. They say that the individual photon pairs produced by each crystal are not entangled with each other. The interference arises not from entanglement, but from quantum indistinguishability, from the fact that the path identity geometry makes it fundamentally impossible to determine which crystal produced which photon. They frame this indistinguishability as a new non-classical resource, distinct from entanglement, capable of producing Bell-violating correlations on its own. The paper's abstract states it directly. They report the violation of the Bell inequality that cannot be described by quantum entanglement in the system, but arises from quantum indistinguishability by path identity, shown by the multi-photon frustrated interference. I want to stop here for a moment and make sure the weight of this lands properly. If this claim is correct, then Werner's theorem has a gap, not a mathematical gap. The theorem itself remains valid, but a physical gap. The theorem says separable states cannot violate Bell inequalities, but the Wang experiment would suggest that nature has found a way to produce Bell-violating correlations without entanglement, using a resource that Werner's theorem does not account for. That resource would be quantum indistinguishability itself, the deep structural fact that identical particles in overlapping paths lose their individual identities. And this is not a small implication. Entanglement is the cornerstone of quantum information theory, quantum computing, quantum cryptography, quantum teleportation. Every protocol in the field assumes that entanglement is the essential quantum resource. If Bell non-locality can arise without it, the entire conceptual hierarchy of quantum information would need restructuring. Bell non-local would no longer be a strict subset of entangled. The nesting would crack, and the definition of what makes a quantum system truly quantum, truly non-classical, would shift underneath the feet of an entire field. But that is only one side of the story, because within weeks, 3 separate groups said the claim is wrong. Now, before I walk through the rebuttals, there is an irony here that I need to name, because it is the kind of irony that the history of Bell's theorem specializes in. The same Zeilinger group, the same intellectual lineage, published 2 earlier papers that describe the exact same path identity mechanism as producing entanglement. Qian and colleagues, Nature Communications, Volume 14, Article 1, 1480, 2023, and Physical Review Letters, Volume 133, Article 233, 601, 2024. In those papers, the same interference phenomenon was described as generating entanglement through path identity. In the 2025 paper, the same phenomenon is described as producing Bell violations without entanglement. The same lab, the same apparatus, the same physics. 2 different descriptions. That discrepancy is not incidental. It is, in fact, the heart of what the rebuttals are about. The first rebuttal came from Ken Wharton at San Jose State University and Hugh Price at Trinity College, Cambridge. Posted to arXiv on the 19th of August, 2025, paper number 2508.13431, with the title Bell Inequality Violations Without Entanglement. It's just post-selection. Wharton and Price are not marginal figures. They are among the leading proponents of retrocausal interpretations of quantum mechanics. They have spent careers thinking about the assumptions that go into Bell's theorem, particularly the assumption of statistical independence, the assumption that the hidden variables are uncorrelated with the measurement settings, and their diagnosis of the Wang result is surgical. They construct a classical electromagnetic hidden variable model, fields plus a threshold detection rule that reproduces Wang's S equals 2.34, a classical model, no quantum mechanics at all. And it works because of one specific feature of the Wang experiment. Whether 4 photons are detected depends on the phase settings alpha and beta. The coincidence rate is not constant across settings. It varies, and that means conditioning on 4 photon coincidences, selecting only the events where all 4 detectors fire, introduces a bias. It is a form of collider bias, the same statistical artifact that epidemiologists worry about in medical studies. The detection probability depends on the settings, which means the hidden variables and the settings are correlated. And that violates Bell's statistical independence assumption. In Bell's formalism, the hidden variable lambda must satisfy P of lambda given A and B equals P of lambda. The hidden variables must be independent of the measurement settings. If they are not, the entire derivation of the inequality fails. And in the Wang experiment, according to Wharton and Price, they are not. The post-selection on 4 photon coincidences creates exactly the kind of setting-dependent sampling that Bell's theorem forbids. The second rebuttal came from Antoni Wojcik and Jan Wojcik. Antoni at Adam Mickiewicz University in Poznan, Jan at the University of Gdansk, both Polish institutions with deep histories in quantum information theory. Their paper appeared on arXiv on the 4th of September 2025, paper number 2509.03127, titled Simple Explanation of Apparent Bell Non-Locality of Unentangled Photons. The Wojcik brothers identify 2 problems. First, the same post-selection issue that Wharton and Price found. But second, and more fundamentally, they argue that alpha and beta in the Wang experiment do not correspond to local measurement settings in Bell's sense. In a genuine Bell test, Alice chooses a measurement setting that determines what she measures on her particle, and Bob independently chooses a setting that determines what he measures on his particle. The settings are supposed to be local operations, but in the Wang experiment, alpha and beta are phases that control the interferometric geometry. They do not select which property of an individual photon to measure. They control the effective source intensity. They change how many photons are produced and which ones are detected. That is a fundamentally different operation than choosing a measurement basis, and it means the CHSH calculation is operationally invalid. And then they drop the deeper bomb. They point out that in the Fock space description of the electromagnetic field, the state in the Wang experiment is mode entangled. The photon number modes of the different crystals are entangled even though the post-selected 4-photon sector look separable in particle language. The distinction between mode entanglement and particle entanglement is subtle, but it is real, and the Wojcik brothers argue that calling the photons unentangled is a labeling choice, not a physical fact. In their words, one cannot claim that the observed interference is due to unentangled photons. One should rather talk here about mode entanglement. And then came the third rebuttal, the one from inside. Das, Karachevsky, Mandarino, Markiewicz, Volontsevitz, and Zukowski, posted to arXiv on the 25th of August, 2025, paper number 250819207, subsequently accepted at Physical Review Letters, Volume 136, Article 090-401, 2026. Marek Zukowski. The name matters. In 1993, Zukowski co-authored a landmark paper with Zeilinger, Horn, and Eckert proposing entanglement swapping, the technique that allows entanglement to be generated between particles that have never interacted. This technique is foundational to quantum repeaters, quantum networks, and the entire field of long-distance quantum communication. Zukowski helped build the intellectual infrastructure that Zeilinger's career stands on. And now Zukowski is in print, saying Zeilinger's latest result does not mean what it claims to mean. I want you to understand how unusual this is. In physics, collaborators do not publicly rebut each other's work unless they believe something important is at stake. The social norms of the field strongly discourage it. You call your former co-author privately. You send an email. You have a conversation at a conference. You do not post a paper on arXiv with a title that is essentially, "You are wrong, and here is why." The fact that Zukowski's group did this, and did it within weeks, and then had it accepted at Physical Review Letters, one of the most prestigious journals in physics, tells you that this is not a minor quibble about data analysis. This is a substantive disagreement about what constitutes a Bell test, and it is happening between people who help define what a Bell test is. The Zukowski group provides an explicit, local, realistic model that reproduces Wang's phase scanning data. They show that the destructive interference effect is real and non-classical in the right sense, but that Wang's analysis of it as a CHSH test is flawed. And then they do something even more pointed. They propose an alternative protocol, an on-off switching protocol, that would generate a genuine loophole robust Bell violation from the same interferometric hardware. In other words, they are saying the physics in your lab is real and interesting, but the way you analyzed it is wrong. And here is how to do it right. That is not a dismissal. That is a correction from a collaborator. And it is perhaps the most damaging kind of critique possible, because it comes with respect, with a proposed fix, and with the implicit message that the error should have been caught before publication. And here is the part that will not leave you alone. Whether the rule held or broke in Nanjing, the fact that the question is open at all means the boundary between a locally real universe and a non-local one is not where you were told it was. It may not be anywhere. I need to go deeper now, because the surface level version of this dispute, the version where either the weighing result is right or the rebuttals are right and we move on, misses the actual implications entirely. Both outcomes lead somewhere unsettling. And to see why, you need to understand what Bell himself thought his theorem meant, because he thought about it more carefully than almost anyone before or since, and his conclusions are not the ones you will find in most textbooks. Bell was, for his entire career, a committed defender of Bohmian mechanics, the de Broglie-Bohm pilot wave theory. This is a hidden variable interpretation of quantum mechanics, originally proposed by Louis de Broglie in 1927 and revived by David Bohm in 1952. In Bohmian mechanics, particles have definite positions at all times, guided by a wave function that evolves according to the Schrödinger equation. There is no measurement problem. There is no wave function collapse. The cat is either alive or dead, never both. The theory reproduces every prediction of standard quantum mechanics exactly, and it is explicitly non-local. The guiding wave, the pilot wave, connects all particles in the universe instantaneously. A measurement on one particle changes the pilot wave everywhere, instantly, affecting the trajectory of every other particle. Bell knew this. He was not a naive realist who thought his theorem had proven Einstein right. He was the opposite. He believed his theorem had proven that reality is non-local in the deepest possible sense, and that Bohm's theory had been right about this from the beginning. In 1982, Bell wrote what may be the most widely read popular paper in quantum foundations. It is called Bertelsmann's Socks and the Nature of Reality, named after his CERN colleague Reinhold Bertelsmann, who had a habit of wearing mismatched socks, one pink and one green. Bell used Bertelsmann's socks as an analogy for EPR correlations. If you see Bertelsmann and notice that his left sock is pink, you immediately know his right sock is green. No spooky action at a distance, just pre-existing sock selection. But Bell's point was that quantum correlations are not like socks. Socks are pre-selected. Quantum correlations cannot be. His theorem proves it. The correlations in quantum mechanics are stronger than any correlation that could arise from pre-existing values. And the only way to explain correlations that strong is non-locality. Something is happening that connects the two measurements, and it happens instantaneously, regardless of distance. His conclusion was stark. It now seems that the non-locality is deeply rooted in quantum mechanics itself, and will persist in any completion. Not might persist, will persist. Bell also detested the vagueness of the Copenhagen interpretation. He despised the words observer and measurement as they were used in quantum mechanics. In his 1975 paper, The Theory of Local Beables, he introduced the concept of beables as opposed to observables. The terminology he wrote, beable as against observable, is not designed to frighten with metaphysic those dedicated to real physics. It is chosen rather to help in making explicit some notions already implicit in and basic to ordinary quantum theory. Beables are things that exist: switch settings, coil currents, dial readings, the stuff that is actually there, before and independent of any observer. And his posthumous paper, Against Measurement, written for a conference he never attended because he died before it was held, is a withering attack on the profession's casual use of the word measurement, as if it were a well-defined concept. It is not well-defined. Nobody can say exactly when a measurement happens. Nobody can say exactly what physical process constitutes a measurement versus a non-measurement. The entire conceptual framework of standard quantum mechanics rests on a word that nobody can define. I am telling you all of this because it matters for the 2025 result. Bell spent his life arguing that the foundational questions of quantum mechanics, the questions about what is real, what is local, what counts as a measurement, are not philosophical decorations on a finished theory. They are open wounds, and the Wang experiment, whatever its ultimate resolution, has reopened one of those wounds in a way that the mainstream had not expected. Because here is what both sides of the dispute agree on, and it is the uncomfortable part. The rebuttals say the Wang result is not a genuine Bell violation. Fine, let us accept that for the moment. What the rebuttals also say, all three of them, is that the reason it is not a genuine Bell violation is that the experimental setup violates one of Bell's assumptions. Wharton and Price say it violates statistical independence through post-selection. The Wojcik brothers say it violates the requirement that the settings be local measurement choices. Zukowski says the analysis framework is wrong and proposes a different one. But think about what that means. The most carefully constructed Bell testing tradition in the world, the lineage that runs from Clauser through Aspect through Zeilinger, the lineage that won the Nobel Prize, has produced an experiment in which the assumptions of Bell's theorem are violated in ways that three separate groups needed weeks of careful analysis to identify. The assumptions are not obvious. They are not written in bold at the top of Bell's paper. They are buried in the mathematical formalism, in conditions like P of lambda given A and B equals P of lambda, in the requirement that alpha and beta correspond to local measurement choices rather than source intensity controls. These are conditions that most physicists working with Bell's theorem every day do not explicitly verify in every experiment. And that should disturb you, because it means the boundary between the rule holds and the rule appears to be violated is much thinner and much more dependent on subtle assumptions than the confident narrative of the 2022 Nobel Prize would suggest. Now let me take this one level deeper, because the Wang experiment, even if it fails as a Bell test, opens a door to a question that Bell himself would have recognized as important. The question is whether entanglement is really the fundamental non-classical resource, or whether there is something deeper underneath it. There is a branch of quantum foundations that says yes, there is something deeper, and it is called contextuality. The idea, originally formulated by Simon Kochen and Ernst Specker in 1967 and dramatically expanded by Robert Speckens in 2005, is that the outcomes of quantum measurements depend on the context in which they are performed, on what other measurements are being performed alongside them, in a way that no classical theory can reproduce. Entanglement in this picture is not the fundamental mystery. Entanglement is just what contextuality looks like when the context is spread across two spatially separated subsystems. Bell nonlocality is a special case of contextuality. And if that is right, then a Bell-like violation without entanglement would not be surprising at all, because the violation would be driven by contextuality, the deeper resource, rather than entanglement, the surface manifestation. In 2008, Klyachko, Khan, Benicioglu, and Shumovsky derived what is now called the KCBS inequality, a contextuality inequality that can be violated by a single quadrit, a three-level quantum system with no entanglement anywhere. This has been experimentally confirmed on superconducting qubits by Jerger and colleagues, Nature Communications, Volume 7, Article 12930, 2016. A single particle, not entangled with anything, violating a non-classical inequality. And in 2011, Samson Abramsky and Adam Brandenberger gave a sheaf theoretic unification showing that Bell nonlocality and Kochen-Specker contextuality are different instances of the same mathematical structure. The boundary between them is not physical. It is geometric. It depends on how the measurement contexts are arranged, whether they are spatially separated or not. If contextuality rather than entanglement is the fundamental non-classical resource, then the entire 2025 dispute looks different. Wang may not have violated Bell's inequality in the strict sense, but what the experiment may have demonstrated, inadvertently, is that the path identity geometry creates a form of contextuality that mimics a Bell violation when analyzed through the wrong framework. The physics is real, the non-classicality is real, the framing is wrong. And that leads to an implication that I personally find harder to sit with than either the Bell is broken or Bell is fine narratives. It means non-locality. The thing that makes quantum mechanics quantum might not live where we think it lives. We have spent 60 years treating entanglement as the magic ingredient. Two particles, carefully prepared, their states correlated in ways that no classical preparation can achieve. That is the standard picture. You need entanglement to see non-locality. You need non-locality to do quantum things. But if contextuality is the real resource, then non-locality is everywhere. It is present in single particles. It is present in unentangled systems. It is present whenever the context of a measurement matters, which is to say, it is present in every quantum measurement ever performed. The spooky action at a distance that Einstein objected to would not be a special feature of entangled pairs. It would be a special case of a deeper property that the universe enforces at every scale, in every interaction, whether you prepare for it or not. The universe would not passively allow non-locality under certain carefully arranged conditions. It would impose it structurally as a condition of its own existence. The fabric of reality would not merely contain non-classical correlations. It would be made of them. And this is the point where I need to connect the physics to the person sitting here listening to this. Because the contextuality result applies to you. You are a quantum system. Every atom in your body is governed by quantum mechanics. Every electron transition that keeps your molecules bonded, every proton in every nucleus of every cell operates under the rules that contextuality describes. If contextuality is the fundamental non-classical resource, then you are not a classical object that occasionally encounters quantum effects. You are a quantum object that experiences the illusion of classicality, because the contextual structure of your internal measurements is arranged in a way that hides its own non-classicality from you. You do not encounter non-locality. You are made of it. That is not mysticism. That is not New Age speculation. That is a straightforward consequence of the contextuality program in Quantum Foundations, supported by published, peer-reviewed results. And it is the kind of implication that the sanitized version of Bell's theorem, the version that says entanglement is weird and leave it at that, was specifically designed to avoid. And this is where I want to come back to Bell, because he would have understood exactly what is happening right now, and he would have had opinions about it. Bell spent his career arguing that the foundations of quantum mechanics were not settled, that the comfortable consensus, the shut up and calculate attitude, was not wisdom, but avoidance. That the real questions, the questions about what is real, what is local, what exists between measurements, were being suppressed not because they had been answered, but because the answers were uncomfortable. He died in 1990 without seeing any of what followed. He did not see the loophole-free tests. He did not see the Nobel Prize. He did not see the 2025 paper that put his name back at the center of the deepest dispute in physics. And he did not see the 3 rebuttals that, in their own way, proved his point more powerfully than any experiment could. Because what the rebuttals demonstrate is that Bell's theorem is not a simple yes or no test. It is a theorem with assumptions. And those assumptions, statistical independence, the locality of measurement choices, the relationship between particle entanglement and mode entanglement, are exactly the kind of foundational questions that Bell spent his life insisting the profession should take seriously, and that the profession spent decades ignoring. The Wang experiment may be wrong. The rebuttals may be right. But the fact that the dispute exists at all, the fact that in 2025 a Nobel laureate's own lab produced data that formally mimics a Bell violation without entanglement, and 3 groups needed weeks to explain why it does not count, that fact is a vindication of everything Bell argued for. The foundations are not settled, the assumptions are not obvious, and the comfortable story, the one where the rule was tested, confirmed, prized, and filed away, was always a simplification. I want to go further now, because there is another layer to this, and it involves what Zeilinger himself thinks about the foundations and how that connects to what his lab just produced. Anton Zeilinger is not just an experimentalist. He has a philosophical position on quantum mechanics, and it is one that makes the 2025 result even more paradoxical than it already is. Zeilinger was born on the 20th of May, 1945, in Ried im Innkreis, Upper Austria. He earned his PhD in 1971 at the University of Vienna under Helmut Rausch, working on neutron depolarization in a dysprosium crystal. He spent years at the Institut Laue-Langevin in Grenoble, did a stint on the MIT faculty in the 1980s, then made a career-defining switch from neutrons to photons at the University of Innsbruck in 1990. His colleague Bertelmann called this switch a considerable risk. It turned out to be the best bet in experimental quantum physics of the past 40 years. The list of things Zeilinger's group has done reads like a Wikipedia page for the entire field. The first experimental quantum teleportation of photons in 1997, published in Nature with Dick Baumeister and Jianwei Pan as co-leads. The first entanglement swapping in 1998. The strict locality Bell test with random analyzer switching in 1998. 3-photon GHZ entanglement in 1999. Carbon-60 fullerene matter wave interference, also 1999. Quantum teleportation 600 meters across the Danube through a sewage tunnel in 2004. The first quantum cryptographic bank transfer on the 21st of April 2004, when €3,000 were sent from a Bank Austria branch to Vienna City Hall using entangled photons. One-way measurement-based quantum computation in 2005. 143-kilometer free space teleportation between La Palma and Tenerife in 2012. And, with his former student Pan Jianwei and the Michus satellite, 1,200-kilometer satellite entanglement distribution in 2017. When journalists ask him what quantum experiments are good for, his standard answer, given in his Nobel interview, is disarming. He says, "I can tell you very honestly and proudly, this is good for nothing. I do it for curiosity, and I think that it has the same use as astronomy. It helps to change our view of the world." He sails a wooden boat named 42 after Douglas Adams. The Austrian press calls him Mr. Beam. He has met the Dalai Lama twice. He collects old maps, but underneath the avuncular persona is a specific philosophical commitment. Zeilinger has long argued that information is the fundamental concept in quantum mechanics, more fundamental than wave functions, more fundamental than particles, more fundamental even than space and time. In a 2005 paper with Kastlav Bruckner, he proposed what they called an informational interpretation of quantum mechanics, in which the wave function does not describe an objective physical state, but rather encodes the information available about a system. Measurement does not collapse a physical entity. It updates information. This matters because of statistical independence. The assumption that Bell's theorem requires that the hidden variables are uncorrelated with the measurement settings is directly connected to a philosophical position that Zeilinger has publicly rejected. The two ways statistical independence can fail are superdeterminism, the idea that the measurement settings and the hidden variables were both fixed by the initial conditions of the universe, and retrocausality, the idea that future measurement choices can influence past hidden variable values. Zeilinger has explicitly rejected both. He organized the Big Bell test in 2018, published in Nature, volume 557, page 212, in which more than 100,000 human volunteers around the world provided random measurement settings by making free choices, specifically to close the freedom of choice loophole and demonstrate that measurement settings are genuinely independent. And now, Wharton and Price, in their rebuttal to Wang's paper, argue that the apparent Bell violation in Wang's experiment is produced by exactly a violation of statistical independence, the same kind of setting-dependent sampling that Zeilinger has spent his career arguing against. I do not know if Zeilinger appreciates the irony. His lab produced a result. 3 rebuttals say the result is an artifact of violated statistical independence. Zeilinger's own philosophical position is that statistical independence must hold. The rebuttals are, in effect, defending Zeilinger's philosophy against Zeilinger's experiment. And the silence from the Wang group makes it worse. No response has appeared as of April 2026. No defense of the result. No engagement with the rebuttals. Nothing. The paper sits in Science Advances. The rebuttals sit on arXiv. One of them is now published in Physical Review Letters, and the gap between them is filled with nothing. I have spent an unreasonable amount of time trying to understand why there has been no response, and I do not have a good answer. It is possible that the authors are preparing a detailed reply. It is possible that they believe the paper speaks for itself. It is possible that internal discussions are happening that have not reached the public record, but the effect from the outside is that the most consequential claim in quantum foundations in the past decade has been met with 3 detailed technical objections and met them with silence. And that silence is its own kind of data point. Because in the history of Bell's theorem, silence has always been the establishment's preferred response to uncomfortable results. Bell's 1964 paper was met with silence. Bohm's 1952 paper was met with silence, followed by exile. De Broglie's pilot wave theory was met with silence at Solvay in 1927. The pattern is so consistent that it has a name in the quantum foundations community. It is called the quantum silence, and it refers to the profession's reflexive unwillingness to engage with results that challenge the consensus framing, even when those results are technically sound. Whether the Wang result is technically sound is precisely the question, but the silence is familiar. Now I want to take the implications in a different direction, because whether or not the Wang result survives, the 2025 dispute has surfaced a question that was always there. lurking under the confident narrative of Bell tests, and it is a question about the relationship between the mathematical formalism and the physical world. Bell's inequality is a mathematical statement about correlations. The CHSH inequality is a mathematical statement about 4 sets of measurements. These are theorems. They are true in the same way that the Pythagorean theorem is true. They cannot be violated by any mathematical construction that satisfies their assumptions. But applying those theorems to physical experiments requires matching the mathematical objects to physical operations. The variable lambda has to correspond to a real physical property. The settings A and B have to correspond to real physical choices. The outcomes +1 and -1 have to correspond to real physical detector clicks. And the sampling has to be fair, meaning that the set of events you analyze has to be representative of the full ensemble. Every one of those correspondences is an assumption, and every one of those assumptions can fail in subtle ways. The detection loophole is a failure of the fair sampling assumption. The locality loophole is a failure of the setting independence assumption. The Wang controversy is, at its core, a dispute about whether the settings in the experiment correspond to the settings in the theorem. And here is the part that most working physicists do not say out loud, but Bell said it explicitly, and it deserves to be heard. The matching between formalism and experiment is never perfect. There is always a gap between the mathematical objects in the theorem and the physical operations in the laboratory. And that gap is where the interesting physics lives. Bell called this the problem of beables. What are the real things, the beables, that the mathematical variables refer to? Is lambda a real hidden variable, or is it a theoretical convenience? Is the measurement setting a real free choice, or is it determined by the prior state of the universe? Is the detector outcome a real event, or is it the result of decoherence in a larger quantum system that includes the detector, the photon, and the experimenter? These are not abstract philosophical questions. They are the questions that determine whether any given experiment constitutes a genuine test of Bell's theorem, and the 2025 dispute is proof that they are not yet answered. Zukowski, in his rebuttal, is essentially saying that the Wang experiment's beables do not match the theorem's variables. The phases alpha and beta are not beables in Bell's sense. They are not local measurement choices. They are source controls, and therefore the calculation of S, while mathematically valid, is physically meaningless as a Bell test. That is a precise, technical objection, and it is also a philosophical one. It is an objection about what counts as a measurement, about what counts as a setting, about what counts as a local operation. It is exactly the kind of objection that Bell spent his career insisting the profession needed to take seriously. And it is being raised by a man who co-authored a paper with the man whose experiment it is aimed at. The family is arguing with itself, and the argument is about what reality is made of. Let me bring this back to you, because there is a tendency, when discussing quantum foundations, to treat the implications as abstract, as something that happens to photons in laboratories and does not affect anything you experience. That tendency is wrong, and I want to explain why. The classical world you experience, the one where objects have positions, where causes precede effects, where what happens here does not instantaneously affect what happens there. That world is an approximation. It is a large-scale averaging of quantum behavior. The table in front of you is made of atoms, and those atoms are governed by quantum mechanics. The light entering your eyes right now is a stream of photons, and each photon obeys quantum rules. The neural signals carrying these words through your brain are electrochemical processes that depend on ion channels. And ion channels are protein structures whose function depends on quantum mechanical tunneling of protons across hydrogen bonds. You are not a classical object observing a quantum world. You are a quantum object experiencing a classical approximation. And the question of whether non-locality is a special feature of entangled pairs or a universal feature of quantum systems is a question about whether the non-classical correlations that define your constituent parts are a curiosity of carefully prepared laboratory states or a structural feature of everything, including you. If contextuality is the fundamental resource, then every measurement your body performs on itself, every neural firing pattern that constitutes a thought, every molecular interaction that constitutes metabolism occurs in a context that affects the outcome in ways that no classical description can capture. The non-classical character of reality is not something that happens in physics labs. It is something that happens in your cells, in your neurons, in the space between the atoms of your DNA, in the ion channels that are carrying this signal through your brain right now. I want to make this concrete because non-classical is abstract and abstractions slide off the mind. Here is what it means in physical terms. Your body contains roughly 37 trillion cells. Each cell copies its DNA when it divides. That copying process involves unwinding a double helix, reading 3.2 billion base pairs, and assembling a complementary strand one nucleotide at a time, using enzymes that operate at the molecular scale. At that scale, quantum effects are not negligible. They are the physics. The hydrogen bonds that hold DNA together are quantum mechanical. The enzyme recognition process, the way a polymerase identifies the correct nucleotide to add, involves quantum tunneling of protons across potential barriers. Errors in that process, mutations, are in some cases driven by proton tunneling events that place a hydrogen atom on the wrong side of a bond at the wrong moment. Every mutation that has ever driven evolution on this planet, every adaptation, every speciation event, every cancer, was downstream of a quantum event. And every quantum event at the deepest level is governed by the rules that Bell's theorem constrains. The correlations that Bell measured between photons 5 meters apart in a Berkeley basement are the same kind of correlations that govern the behavior of protons in the hydrogen bonds of your DNA. They are the same kind of correlations that determine whether a mutation happens or does not happen in a cell that is dividing inside you right now. At this moment, as you listen to this, you are not a spectator watching quantum mechanics from a safe distance. You are a quantum mechanical process. And the question of whether the non-classicality that Bell's theorem reveals is limited to entangled laboratory systems or extends to every quantum interaction in the universe is a question about what you are. And you have never been told this. Not because it is controversial, not because it is speculative, but because the implication is so far outside the standard educational narrative that the people who teach quantum mechanics would rather skip past it than explain what it actually means for the experience of being a physical object in a non-classical universe. That is the invisible scandal. Not that the information was suppressed, but that it was omitted. That the safe version of the story, the one where Bell's theorem is about entangled photons in laboratories and has nothing to do with you, was the only version that made it into the public conversation. And the full version, the one where the non-classicality extends to everything everywhere, including the person sitting here right now, was left out because it was too uncomfortable to say out loud. And this brings me to the question that I think sits underneath the entire 2025 dispute, the question that neither the Wang paper nor the 3 rebuttals fully addresses, the question that Bell himself would have asked if he were alive to read any of it. What is the relationship between non-locality and reality? Because there are multiple interpretations of quantum mechanics, and they disagree about almost everything. They disagree about whether the wave function is real. They disagree about whether particles have positions between measurements. They disagree about whether the universe splits every time a quantum event occurs. They disagree about whether consciousness plays a role. They disagree about whether the past is fixed. But there is one thing they all agree on, every single one of them, and it is the uncomfortable part. They all agree that Bell's inequality is violated. Every interpretation reproduces the predictions of quantum mechanics, and quantum mechanics violates Bell's inequality. That means every interpretation, without exception, either gives up locality or gives up realism or gives up both. Let me walk through them, because the unanimity is the point. Copenhagen, the standard textbook interpretation, the one you were probably taught if you took a quantum mechanics course, gives up realism. In Copenhagen, particles do not have definite properties until they are measured. The wave function is a tool for calculating probabilities, not a description of something real. And when a measurement happens, the wave function collapses randomly to one of its possible values. Copenhagen saves locality at the cost of saying that nothing is real until it is observed. Many worlds, the Everett interpretation, proposed by Hugh Everett III in 1957, gives up a single reality. In many worlds, every quantum measurement causes the universe to branch into multiple copies, one for each possible outcome. All equally real, the wave function never collapses. Locality is preserved within each branch, but the price is that there are uncountably many copies of you, right now, having every possible experience simultaneously. And the personal cost of proposing this idea was enormous. Everett submitted his thesis at Princeton under John Archibald Wheeler, who supported the idea but could not protect Everett from the establishment's reaction. Niels Bohr was dismissive. The broader community ignored it. Everett left physics entirely, taking a job at the Pentagon doing defense analysis, and never returned to academic physics. He became an alcoholic. He died in 1982 at the age of 51 of a heart attack, alone in his home. His daughter, Elizabeth Everett, took her own life in 1996, leaving a note saying she wanted to be in the right universe with her father. His son, Mark Oliver Everett, who would go on to front the rock band Eels, later said he had to learn about his father's work from a BBC documentary because his father never talked about physics at home. That is the human cost of proposing an uncomfortable interpretation of quantum mechanics. Not disagreement, not debate, exile, and then death. Bohmian mechanics, Bell's preferred interpretation, gives up locality explicitly and unapologetically. Particles have definite positions at all times, guided by a pilot wave that connects them all instantaneously across the entire universe. A measurement on a photon in your lab changes the pilot wave everywhere, including at the other end of the observable universe, right now. The theory reproduces every prediction of quantum mechanics exactly. It has no measurement problem. It has no ambiguity about what is real. Particles are real. Positions are real. The pilot wave is real. And it was dismissed by the establishment, first when de Broglie proposed it in 1927, and again when Bohm revived it in 1952. Robert Oppenheimer called Bohm's version juvenile deviationism, not because it was wrong, not because it made incorrect predictions, not because it had mathematical flaws, because it was non-local, and non-locality was uncomfortable, because it gave particles positions, and positions were unfashionable, because it answered the measurement problem, and the measurement problem was supposed to be unanswerable. The reason you have never heard of Bohmian mechanics in school is not that it was disproven. It is that the implication was too uncomfortable. Cubism, the quantum Bayesian interpretation developed by Christopher Fuchs, Rüdiger Schack, and David Mermin, gives up the idea that quantum states describe objective reality at all. In cubism, the wave function is a personal tool, like a degree of belief. Quantum mechanics is about an agent's expectations for future experiences, not about an observer, independent world. Bell's theorem in this picture does not reveal non-locality. It reveals the limits of classical reasoning about quantum experiences. Relational quantum mechanics, proposed by Carlo Rovelli in 1996, says that quantum states are not properties of systems, but properties of the relationship between systems. The photon does not have a definite polarization. The photon relative to the detector has a definite polarization, and that relation is not shared with the photon relative to a different detector until the two detectors interact. Bell violations in this picture arise because the correlations between relations are stronger than the correlations between properties. Retrocausal interpretations, the kind advocated by Wharton and Price, the same physicists who rebutted the Wang result, give up the idea that causes must precede effects. In a retrocausal picture, the future measurement settings can influence the past preparation of the particles. Bell's statistical independence assumption fails, and the inequality can be violated without non-locality, because the correlation between settings and hidden variables is built into the causal structure of space-time itself. That is 6 interpretations. They disagree about everything. Whether the wave function is real, whether particles have positions, whether the universe is one or many, whether time has a direction, whether reality exists independently of observation. But they all agree that Bell's inequality is violated. Every single one of them predicts correlations stronger than any local realistic theory can produce. The violation is not interpretation dependent. It is a fact of the formalism, and every interpretation pays a price for it. Every one of them gives up something that you intuitively believe about the world. And here is the consensus flip that makes this worse. All 6 interpretations also agree on something else. They all agree that the violation is not about consciousness. The popular version of quantum mechanics, the one that shows up in documentaries and self-help books, says that consciousness collapses the wave function, that the observer creates reality, that your mind shapes the physical world. Not a single serious interpretation of quantum mechanics supports this. Not Copenhagen, which defines measurement without reference to consciousness. Not many worlds, which has no collapse at all. Not Bohmian mechanics, which has no observer-dependent anything. Not cubism, which is about agents, but not about consciousness in the metaphysical sense. Not relational QM, which is about physical interactions between systems, not about minds. The one thing everyone agrees on is the thing nobody wants to say. The violation of Bell's inequality the most thoroughly confirmed experimental result in the history of physics, proves that reality is not locally real, and consciousness has nothing to do with it. The universe is doing something that violates your deepest intuitions about how the world works, and it is doing it whether anyone is watching or not. The observer is irrelevant. The violation is structural, and you were never told this because the pop science version, the one where your mind matters, sells better than the real version, which is that you do not matter at all. Not to the violation, not to the correlations, not to the structure that enforces them. The universe is not responding to you. It is not waiting for you to look. It is non-classical, all the way down, in every interaction, at every scale. And your experience of a classical world is an emergent approximation that has nothing to do with your consciousness and everything to do with decoherence, the process by which quantum systems lose their coherence through interaction with their environment. Your brain does not collapse wave functions, the environment does, and it does so whether you are paying attention or not. That is what Bell's theorem actually says when you follow it all the way to the bottom. Not that the universe is mysterious, not that quantum mechanics is weird, but that the classical reality you inhabit is not fundamental. It is a surface, and underneath that surface, the real structure, the one that Bell's inequality probes, does not obey the rules you were taught. And the 2025 dispute is a reminder that we are still mapping that structure, still arguing about what the rules are, still discovering that assumptions we treated as settled were more fragile than we knew. I want to end where this started, with a man in Belfast who could not afford grammar school. John Stuart Bell worked on the foundations of quantum mechanics as a hobby because his profession considered it unworthy of serious attention. He published his most important paper in a journal that folded. He received 92 citations in 18 years. He never discussed his work with his colleagues. He died of a cerebral hemorrhage at 62, reportedly on the Nobel shortlist, and the prize came 32 years later for 3 men who tested what he proved. And right now, in 2026, the theorem he derived on evenings and holidays is at the center of the most consequential active dispute in physics. A Nobel laureate's laboratory has produced data that looks like it violates his rule without entanglement. 3 groups say the data does not mean what it appears to mean, and nobody can agree on why. Because the assumptions of the theorem, the assumptions Bell spent his life arguing were more important than anyone admitted, turn out to be exactly as subtle and exactly as easy to misapply as he warned. 62 years after his paper, 36 years after his death, the rule is alive. It is still the sharpest blade in physics, and the people holding it are not sure they are holding it by the handle. Bell wanted to know what is real, not what is measurable, not what is observable. What is real, what exists when nobody is looking, what the beables are. And he proved, with 6 pages of mathematics, that whatever is real, it is not locally real. Something is happening in every entangled system, possibly in every quantum system, that connects distant events instantaneously or retroactively, or through a splitting of worlds, depending on which interpretation you prefer. But it is happening. That is not in dispute. That has never been in dispute. And the 2025 result, whether it stands or falls, has not changed that. What it has changed is the confidence, the comfortable confidence that we knew exactly what was required to make it happen. Entanglement, we said, You need entanglement. Werner proved it. 60 years of experiments confirmed it. Nobel Prize honored it. Case closed. And then a lab in Nanjing got S equals 2.342 without it. And 3 groups needed weeks of detailed analysis to explain why it does not count. And the explanation involves assumptions so subtle that even the architects of modern Bell testing had not noticed they were being violated. The rule holds, probably, for now. But the ground it stands on turned out to be less solid than the textbooks suggest. And the man who first found that ground, who first realized that the foundations of quantum mechanics were not as firm as everyone pretended, who worked on it in secret because his colleagues would not have understood. That man has been dead for 36 years, and he still has not been proven wrong about the thing that mattered to him most. The foundations are not settled. They never were, and every physicist who has ever told you otherwise was either lying or had not read the right 6 pages. The rule Bell gave us is still doing its work. It is still cutting. And right now, it is cutting in a direction that nobody expected, into the space between what we measure and what we assume, between the theorem and the laboratory, between the mathematics and the beables. Bell's inequality was never just a test of local realism. It was a test of whether physics had the courage to face what its own formalism was saying. And in 2025, 62 years after a working-class kid from Belfast wrote 4 pages in a dying journal, that test is still running. The result is still coming in. And the implications, the ones that reach all the way from a photon in a nonlinear crystal to the atoms in your body to the structure of reality itself, have not been absorbed yet. They may never be. And that is not because the answer is unknown. It is because the answer, as Bell suspected from the beginning, may be worse than the question. There is a street at CERN's Maren site called Route Bell. It runs past the buildings where he worked on accelerator physics by day and hid his real work at night. In Belfast's Titanic Quarter, there is a semicircular road called Bell's Theorem Crescent, completed in 2015, the same year the loophole-free tests sealed the case his theorem had opened. On the site of his old Belfast Technical High School, there is a student residence called the John Bell House, completed in 2016. The University of Toronto awards the John Stuart Bell Prize, created in 2008. Alain Aspect personally presented the first one to Nicolas Gazin in 2009. The 4th of November is informally called Bell's Theorem Day. Queen's University Belfast has a lecture theatre with his name on it. A street, a crescent, a residence hall, a prize, a day, a lecture theatre, all named after a man who never discussed his most important work with his colleagues, because they would have thought less of him for it. And right now, in the laboratory in Nanjing, the apparatus that produced S equals 2.342 without entanglement is still standing. The crystals are still aligned. The detectors are still calibrated. The data is still in the files. And the question it raises, the question of whether entanglement is truly required for Bell nonlocality, or whether something deeper, something structural, something that cannot be turned off, is responsible for the correlations that make the classical picture of reality impossible. That question is open. The rebuttals say the answer is no. The result is an artifact and the standard picture holds. The paper says the answer is yes. The result is real, and something fundamental has shifted. Neither side has blinked. Neither side has responded to the other. The most consequential debate in the foundations of quantum mechanics is happening in the space between a published paper and 3 unpublished critiques, and the rest of the world is talking about something else entirely. Bell would have recognized this silence. He lived inside it for 30 years. The rule he gave us is still the sharpest blade in physics. It cuts between what we want to believe about reality and what the data actually says. It has cut through local realism, through hidden variables, through every attempt to rescue the comfortable classical picture of a universe where objects have properties and causes precede effects. And what happens here stays here. And now it is cutting in a new direction, into the space between entanglement and indistinguishability, between particle descriptions and mode descriptions, between what we measure and what we assume we are measuring. And the man who forged that blade, the working class kid from Belfast who could not afford grammar school, who proved the most important theorem in quantum mechanics on his evenings and holidays, who never discussed it with his colleagues, who died at 62 with a brain hemorrhage, while the Nobel Committee was still decades away from recognizing what he had done. That man is not here to see any of this. He is not here to read the Wang paper. He is not here to read the rebuttals. He is not here to weigh in on whether path identity constitutes a genuine, non-classical resource or a misidentified form of mode entanglement. But his theorem is here. It is still working. It is still forcing the question. And the question is the same one he asked in 1964, in 6 pages, in a dying journal, in a field that did not want to hear it. What is real? Not what is measurable. Not what is observable. Not what is practical or useful or fundable. What is real? The answer, 62 years later, is still coming in. The rule has not been broken, but the confidence that we knew exactly what it was protecting, exactly where the boundary sat, exactly what was needed to cross it, that confidence is gone. And the atoms in your body, the ones that were here before you were born and will be here after you are gone, the ones that are right now participating in quantum interactions governed by the same formalism that Bell's inequality constrains, those atoms do not care about your confidence. They do not care about the Nobel Prize. They do not care about the rebuttals. They are doing what they have always done, obeying rules that are not locally real in ways that no classical description can capture, in a universe that decided the answer to Bell's question long before anyone was around to ask it. You were just never told.